Hello everyone, and welcome back to Mitchell's Physics Review. Today we'll be working on RL circuits. At the moment t equals 0, a 20-volt battery is connected to a 5 millihenry coil and a 6 ohm resistor. Now, let's just take a glance at part A and B. Immediately thereafter, how does the potential difference across a resistor compare to the EMF across the coil? And answer the same question about the circuit several seconds later. Now, this may seem like it has a lot of math involved, but I promise you it doesn't. There's actually a really simple way we can find out the answers to all four of these questions, and that is through a graph. So let's start by drawing a voltage versus time graph. To start, in an RL circuit, we know that the voltage will be approaching an asymptote, which would be the max voltage of 20 volts. We also know that the coil is going to start at the max voltage as soon as the circuit is opened, or when t is essentially extremely close to 0. Now, why is that? That's because the coil, or the inductor, is trying to resist a change in current. So when that circuit is completed, there's going to be a high potential difference as that current rapidly increases, meaning the coil will be at the highest resistance, trying to make it to steady state, meaning all the voltage is going to go across the coil. Meanwhile, while all the voltage is across the coil, none will be across the resistor, so it's going to be at 0. As time increases, however, the coil slowly transitions into steady state and goes down to 0 volts after the current reaches a complete steady state. If the coil then reaches 0, all the voltage is going then through the resistor instead. So, now let's take a bigger look at part A. Once again, the question, immediately thereafter, how does the potential difference across the resistor compare to the EMF across the coil? Well, from our graph, we know that the resistance will be 0 volts initially, and the coil should be at 20 volts initially. I also set up a little bit of the math if it helps you to understand better. At t equals 0, essentially, the initial current would be 0, and we just use the equation V equals I times R. 0 times the 6 ohms of the resistance is just going to become 0 volts. Now to part B. Answer the same question about the circuit several seconds later. Once again, we're going to use our graph for this. After time has progressed for a while, we see the coil is approaching 0 and the resistor is approaching 20 volts. So, our resistor should have 20 volts and our coil should have 0 volts. Why is this? Well, once again, as I previously stated, the current is now in a steady state after several seconds have passed, meaning it has no resistance. So the total EMF should be on the resistor or across the resistor instead of the coil. Now to part C. Is there an instant at which these two voltages are equal in magnitude? Well, see how handy this graph was? There is an instant where these two voltages are equal in magnitude because there's an instant where they both cross. So for part C, as shown by the graph, there will be an instant the voltages are the same. Now on to part D. If so, when? Is there more than one such instant? Well, in this case, we're only going to see one instance of the voltages being exactly the same. And we're also able to calculate the time at which the voltages are the same. So, let's take a look. We're going to start by using the equation EMF is equal to EMF naught times 1 minus E raised to the negative RT over L. So, first we can plug in all of our givens. On the right side of 20 volts, 6 ohms, and 5 times 10 to the negative 3rd henries. But how did I get to this left side of 10 volts? Well, I got to 10 volts, and this is how. Since both the voltage across the coil and the resistance are increasing and decreasing at the same rate, they should be equal at EMF max over 2. 20 over 2 is just 10 volts. After that, I plugged into my calculator and got the time is equal to 0.578 milliseconds. Finally, time for part E. After a 4.5 amp current is established in the resistor and coil, the battery is suddenly replaced by a short circuit. Answer questions A and B again with the reference to this new circuit. Now, this graph right here won't be helpful anymore because we are now almost going to reverse the graph. We're going to see this as a new circuit with only the resistor and the inductor in a loop with an initial 4.6 current. Remember, since the 4.6 amp current is established, it's at steady state, meaning that the EMF should only be in the resistor at that point. So, we can do it VI, or V instant is what I'm calling it, and plug in the current 4.5 and 6 ohms, and then multiply them together to get 27 volts at the instant. However, after a long time passes, the current is slowly going to be decreasing, meaning that the inductor is going to gain more volts. So, after several seconds have passed, or VA, the current will then be 0, the resistance will then be 6 ohms, and the voltage across the resistor after several seconds have passed will be 0 volts. From this problem, I learned the importance of using a graph. Could you imagine all the work it would have taken to calculate each one of those and how many different equations we would have had to write if we didn't draw that single graph? So, I hope in the future, if you're met with a problem, you take a look at its graph first, and you might find an easier way to solve it than you might think. I hoped this video helped you, like it helped me realize the importance of graphing first and understanding the graph. Have a good day.